Hello everyone, I Anju Joshi, working as an assistant professor in the Department of Computer Science and Engineering from ABES Engineering College, is going to deliver a lecture on the concept of Armstrong axioms. So in the previous video lecture, I have already discussed about the concept of functional dependency, what are the types of functional dependencies, how can we determine whether a given functional dependency is valid or not, and we also solved some practice problem related to the concept. So today, moving on, I'm going to discuss about the concept of Armstrong rules, what are the different types of Armstrong rules, and some practice problem related to it. So let's get started. Okay. So Armstrong rules were basically developed by William W. Armstrongs. So before starting what Armstrong rules is all about, let me discuss what axiom or rules is. So axiom is basically a statement that is taken or considered to be true and which serve as a premises or a starting point for further argument or for further analysis. So Armstrong rules are the basic principles that holds on every relational database and can be used to generate the closure shape. So this is a concept that I'm going to discuss in the upcoming video lecture. So these are the basic fundamental rules with the help of which we can understand the concept of closure and we can have a better understanding of functional dependency as well. So let's see what are the different types of Armstrong rules. Okay, so the Armstrong rules are basically divided into two categories. The first category is called as primary rules, and these are the three listed rules that comes under the primary rules. And the second category is called as secondary rules. So we'll discuss these rules one by one. Okay. So primary rules are basically the completely fundamental rules, and with the help of which we can also derive secondary rules. Okay, so the first rule that I'm going to discuss today is called as reflexivity. So according to by the definition, it says that if x and y is a set of attributes and x and y belong to a relation R, and if y is a subset of x, then we can say that x implies y. Let's understand this logic of reflexivity rule first. So according to this reflexivity rule, if x and y are two attributes, okay, attributes, and they belong to relation R, and if y is a subset of x, then a function dependency will hold from x to y. Let's understand this with the help of an example. Let's suppose x equal to ABC attribute and y equal to AB. And according to the rule, we can see that y is a subset of x. It's already visible. Y is a subset of x. Then we can say that x implies y. It is clearly a case of trivial function dependency that I've already discussed because we can say that ABC implies AB. As we can clearly see that ABC is already available. So from ABC, we can clearly determine AB. So here the same logic of trivial function dependency is called as reflexivity. Okay. All right. So the next rule says that, okay, so the next rule is augmentation. It also comes under the category of primary rule of Armstrong. Let's see what augmentation rule is all about. So according to the augmentation rule, if x implies y or if x determines y and z is another set of attributes, then we can write or we can say that xz implies yz. Let's understand this logic. So according to the rule, it says that x implies y. So we can already determine y through x. Okay. So can we append another attribute that is z on the both side of FD? Yes, we can do so. We can append attribute z on both side of the FD. It will not make any issue. Okay, because it will not bring any load or any change on the given function dependency. So we can easily append another attribute z on both sides of it. So this is called as augmentation. Okay. So the next rule that we are going to discuss today is transitivity rule. According to the transitivity rule, it's the most simplest rule. It says that if x implies y and y implies z, then we can also say that x will determine z. Okay. So the x will determine z. So it's a simple rule. It just says that if x implies y and y implies z, then we can write it as x implies z. This can be logically implied or inferred from this given set of function values. Alright, now let's discuss the second rule. So these were the primary rules: reflexivity rule, augmentation rule, and transitivity rule. Now we are going to discuss the secondary rules. So the first rule that comes under the category of secondary rule is union rule. And by the definition, it says that if x and y are the two attributes, okay, if x and y, x, y, and z are three attributes, and if there is a function dependency, or we can say that x implies y or x determines y, x determines z, then we can write that as x determines y. See, understand this. X can already determine y, it is already given, and x can already determine z as well. So we can combine both y and z and can write it like this. There is no issue. So this rule is called as union. Okay. The next rule that comes under the category of secondary rule is decomposition rule. It is a reverse of union. Okay. If it says that if x implies yz and x imply, okay, if x imply yz, then we can also write it as x imply y, then x imply z. We can already see that from x we can already determine y and z. So we can write these as two separate function dependencies. Again, there will not be any issue. To understand this concept of union and decomposition rule more clearly, let's take an example. Let's suppose this is a given function dependency. AB implies CETL. So we can write it down as AB implies C and AB implies. Clearly in this function dependency, we can clearly apply union and decomposition. Okay. So if we write C and D separately, then it will be called as decomposition. And if we combine both C and D attributes together, then it will be called as union. One point that should be noted is that union and decomposition rule can always be applied on the right hand side of the production. Should always be applied on the right hand side of the production. Why so? Let's check through the example that why cannot be applied union and decomposition rule on the left hand side. Let's consider this example. AB implies C. So this function dependency is given to us that from AB we can determine C. So can we write it as A implies C and B implies C? Can we decompose it? Is it possible? The answer is no. Absolutely not. Why so? See, this example says that when we have both A and B, then only we can determine this attribute C. While this two functional dependency says that only through A or only through B we can determine C, which is logically incorrect. Okay. So we cannot apply decomposition on the left hand side. Let's check the case of union as well, whether we can apply union on the left hand side or not. Let's consider these are the two functional dependency. A can determine C and B can determine C. From A to C, from B to C. Can we write this function dependency as AB to C? Yes, we can do so, but the problem is it will be again, it's like that. See, here in this example, we are saying clearly we can see that from either from A or B alone, we can determine C. Okay, but here we are making our FD weaker by saying that only when we have both the attributes A and B, then only we can determine C. So we are making our FD weaker. That's why union should not be applied. Union rule should not be applied on left hand side of the functional dependency or the production. Okay, I hope it's clear. The last category of secondary rule that we are going to discuss today is called as pseudo transitivity. According to this rule, if X can determine Y and if WY can determine Z, then we get this function dependency, or we can write it as WX can determine Z. So actually we need a dependency from WX. So how to prove it is correct or not? Let's see here. Here it is given X can determine Y. So can we append W on both the side of the function dependency? Yes, we can do so by using augmentation. So we will append. WX determine W using augmentation rule that we have already discussed. Okay. Now, here it is given that from WY we can determine Z. So from WX we can determine WY, and from WY we can determine Z. So it clearly becomes the case of transitivity. Here we can apply transitivity and we can conclude that from WX we can determine WZ. So this is what pseudo transitivity is all about. So here we discuss two important rules, two category of rules. First is primary rules, that is reflexivity rule, augmentation rule, and transitivity rule with the help of examples. And then we discuss the next set of rules called as secondary rules, which are union rule, decomposition rule, and pseudo transitivity. Okay, so earlier, see this point, I've written here that these axiom rules can also provide a technique to identify a set of functional dependencies that are hidden, that is not given in the relational schema. Okay, so with the help of these rules, we can also find the functional dependencies, hidden functional dependencies. How we can do so? Let's check this practice question and see how can we find out, or how can we determine the hidden dependencies which are not given in the relational schema. So the question says that suppose R is a relation with a set of attributes A, B, C, D, E, F, and here we have given the identified set of function dependencies which are as follows. Okay, so these are the function dependencies that is given, and we have to find the hidden function dependencies with the help of Armstrong rules. So check here. First function dependency, there is a function dependency from A to B, and there is a function dependency from A to C. So can we combine these two? Yes, we can do so with the help of union. So the function dependency from A to BC can be inferred from the given set of function dependency. This is given, this was hidden. So we find out this hidden function dependency with the help of union rule. Okay. So the next hidden function dependency that we can find out from this given set of function dependencies with the help of Armstrong rules is, see this. There is a function dependency from A to B given here, and there is a function dependency from B to B. This becomes the case of transitivity, so we can infer that from A we can also determine. So we were able to find out this function dependency with the help of transitivity that we have studied earlier. So the next hidden dependency that we can find out from this given set of function dependency is check. See here. Here we have, here it is given A to C and CD to. Okay. So can we append D on both the side of this function dependency? Yes, we can do so. We can append D. We can append D here by using augmentation. Okay. AD to CD and CD to. Now, here we can see that it through transitivity rule, we can say that AD implies. So this rule we have already started. This is called as pseudo transitivity. So through pseudo transitivity, we can imply that from AD we can determine F as well. Okay. So as we can see that with the help of the Armstrong rules, we can understand, we can find out, we can have the better understanding of functional dependency, as well as we can find out the hidden dependencies from a given relational schema. This concept will also be useful in the determining the closure of attribute set, which we will discuss in the next lecture. So that's all from my side. Thank you.